In this video, I want to present an alternative flowchart and model different from that which is presented on page 95 of Carey. In my mind, it has a simpler likelihood function that is more similar to that we saw when we went over Krushke's text. But again, it's going to be a very similar scenario in that what we're interested in is a t-test where we've got male and female falcon wing lengths, and we're interested in the difference. So as I said, the difference between what I'm presenting now and what was in Carey is in the likelihood function. And here's our likelihood function right here that says that 100 different individual observations in wing length are going to come from a normal distribution with some value mean, and this indicates that the value of that mean is going to vary with sex. And in fact, what we're going to find is that for the males, it's going to be mu2, and for the females, it's going to be mu1. So those are the means of the normal distributions from which the individual observations arise. And again, normal distributions in JAGs are parameterized by tau. As in the last video, we're going to use the approach associated with the generalized linear model that says again that the individual observations arise from a normal distribution with some value mu, which is going to be this and this for males and females respectively. So they're potentially going to have different mu's. They will have different mu's, but they're going to have a constant variability, which again in JAGs is parameterized by tau, which is equal to the reciprocal of the variance. So one of the things we're going to have to do in order to make this work is there's some code that says we're going to take this thing sex, which currently is a character, and we're going to make it into a factor, which means it's going to be stored as a number. And so the way R works is that when it establishes numbers associated with a character, it's going to work alphabetically. So the number 1, once I create sex now being a factor as opposed to a character, the number 1 is going to be associated with female, and the number 2 is going to be associated with male. Now when you notice, I'm going to talk about some more data manipulation that's done, but essentially what JAGs is going to operate is going to be on a list that looks something like this. It has Y, which is 100 values, the first 60 of which are males, although that's not really going to matter too much here, and the last 40 are females. It's going to have this newly created thing called sex. And again, you notice that it leads with 2's because 2's are there. And then I create these two new variables, n-sex representing the number of sexes, which is 2, and n-sub, the number of subjects, which is 100. So here's our model. Again, we start with open quote, the word model, open curly brace, close curly brace, close quote. So that's our model. And what we have in this block here is a for loop with its opened and closed braces. And this is our likelihood function. So as we saw, the individual observations are deemed to arise from a normal distribution that has a mean that will vary with sex and variability that is parameterized by tau, which is the inverse of variance. The challenge here, as before, the thing I always struggle with is this double square bracket nested indexing. So let's do a review once more of how that would work. So we've got these y values arising from a normal distribution where the mean is specified this way. So let's see how that would work. So we've got mu sex I. So this loop is going to go through all 100 subjects. So if you think of our subjects here, I tend to think of them, this may not actually be totally correct, but the way I tend to think of it is we've got this implicit indexing where I goes from 1 to 100. So what happens when I is equal to 1? When I is equal to 1, we've got mu sex 1. So there is I is equal to 1. What is sex? It's the value of sex when I is equal to 1. That's going to be mu 2, which is going to be equal to the males. In contrast, when I is equal to 2, we're going to have mu, excuse me, I shouldn't do 2, I should do 99. It's 99. When we've got mu sex 99, what do we get? Well, when I is equal to 99, sex is equal to 1. So we get mu at 1, which is equal to the female. So that's our likelihood. And now we've got to establish some priors. So we need our priors for mu. And we're going to need two priors because we've got two values of mu. And we're going to set fairly diffuse priors. Now, one way I could do it is to say, okay, mu 1 is equal to that. And I could say mu 2 is equal to, and just repeat it that way. And that would work pretty well, given that I've only got two sexes. But oftentimes, when we're going to have a situation in which you got more than one sex or more than one item that we got to loop through, it's far more efficient to do a loop. So I'm going to say from 1 to 2, again, there's the open, close curly braces. The prior, we're talking about priors now, the prior for mu, and it's going to loop through 1 and 2 in both cases, is going to be this. So that's this gives us the priors for mu, and then we need our priors for tau, because again, somewhat strangely, JAGS parameterizes the variability in a normal distribution by this parameter tau. So we use this two-step approach where first we say that the value of sigma arises from a fairly diffuse prior, and then we calculate 1 over sigma squared to give the value of tau. So this is how we create the priors for the variability. And finally, if we're interested in the difference between the male and female wing lengths, we create this derived quantity because mu at 2 is the male wing length and mu at 1 is the female wing length. So this is just an alternative approach that is more similar to Krushky in terms of the likelihood function, a little bit different from what we saw earlier, which was what Carey used.